Hello students, in this lecture we have to discuss the topic first law of thermodynamics. This topic is a part of heat and thermodynamics. Now there are some prerequisites of this topic. All of thermodynamics can be expressed in terms of four quantities. These are temperature, internal energy, entropy, and heat. The objective of this topic is thermodynamics is the study of the relations between heat, work, temperature, and energy. The laws of thermodynamics describe how the energy in a system changes and whether the system can perform useful work on its surroundings. Now, we discuss the introduction. Thermodynamics is the branch of science that deals with energy levels and the transfer of energy between systems and between different states of matter. According to British scientist C. P. Snow, the three laws of thermodynamics can be humorously summarized as you cannot win, you cannot even break even, you cannot get out of the game. On this slide, we consider we cannot win. That is first law of thermodynamics. The first law of thermodynamics is an extension of the law of conservation of energy. The change in internal energy of a system is equal to the heat added to the system minus the work done by the system. That is delta U is equal to Q minus W. On this slide, we consider what is energy in the language of great physicist Richard Feynman. It is important to realize that in physics today, we have no knowledge of what energy is. We do not have a picture that energy comes in little bouts of a definite amount. It is not that way, according to Richard Feynman. However, Feynman goes on to elaborate that energy has meaning as a way to define and quantify changes which bring about changes between systems, energy levels, or states of matter, that is, for any reaction. How seriously must we take the physical existence of this energy no more and no less than any other bookkeeping practices, according to Richard Feynman. Now we discuss the systems in the sense of thermodynamics. System, the part of the universe that is under consideration. It is separated from the rest of the universe by its boundaries. Open system, when matter can cross the boundary. Closed systems, when matter cannot cross the boundary. Isolated system, boundary seals matter and heat from exchange with another system. Here, the pictorial representation is also given for open, closed, and isolated system. On this slide, we take two important processes, adiabatic and isobaric. The way a system changes states. First, adiabatic. No heat exchange across boundaries of a system, and isobaric, in this case constant pressure, but boundaries of the system can change. That is, we can change the volume. On this slide, we discuss the term heat. It is very important term in thermodynamics. The origin of thermodynamics deals with heat. Thermo considers heat and really any energy as though it were an invisible truth, always following from higher to lower energies. Therefore, signs are positive when energy flows from surroundings to the system, and we take negative sign when energy flows from system to surroundings. Now we discuss the term work on this slide. Work is another kind of energy different from heat, can flow in and out of a system and invoke changes. Imagine the energy required to lift a book. That work changes the potential energy of the book but is not related to heat. On this slide, we discuss the term internal energy. It is represented by the letter Q. Changes in internal energy, and we can write here dU or delta U are positive if energy of a system increases. Energy here as heat added, equal or plus work done on the system plus sometimes it has been formulated that work done by a system is positive in energy change. The sign of arrow not how we have it formulated above. Difference in perspective. Be careful when reading other sources. This sign, that is, sign of arrow, change confusion propagates through the rest of thermodynamics. On this slide, we discuss mechanical work description. First is work. Work is equal to force required to move a body and multiplied by distance that body is moved. We can write here W is equal to sine of integration with lower limit x naught and higher limit x f dx because F is equal to PA, that is force is equal to pressure per unit area. Then we can write here W is equal to sine of integration with lower limit x naught, higher limit x f dx is equal to minus PA into x minus x naught is equal to minus PdV. This describes a piston's movement and potential energy. Now we discuss first law of thermodynamics, also known as the law of conservation of energy. Gibbs in 1873 stated energy cannot be created or destroyed, only transferred by any process. The net change in energy is equal to the heat that flows across a boundary minus the work done by the system. That is, delta U is equal to Q plus W, where Q is heat and W is work. Some heat flowing into a system is converted to work and therefore does not augment the internal energy. On this slide, we take here work and the first law. We can think about work as a function of pressure and volume, that is dW is equal to PdV, where PdV is the incremental small change in volume at pressure associated with force into distance, dimensions of work. Restate the first law as du is equal to dq minus pdv. Here, the pictorial representation also given. Now, we discuss the term enthalpy and it is represented by the capital letter H. H is equal to U plus PV. Total differential for enthalpy is dH is equal to du plus pdv plus vdp for our integrated change in state previous. H1 is equal to U1 minus PV1 and H2 is equal to U2 minus PV2. That is delta H is equal to H2 minus H1 and it is represented by Qp, that is at constant pressure and volume. Recall that energy is not known, only the change is meaningful. Therefore, change is measured from a reference state with sign of arrow, pure elements 25 degrees Celsius, 1 bar pressure have an enthalpy of 0 and it is represented by H0F. On this slide, we take some questions for the practice. First is 5,000 joules of heat are added to 2 moles of an ideal monoatomic gas initially at a temperature of 500 Kelvin while the gas performs 7,500 joules of work. What is the final temperature of the gas? Second question, compute the internal energy change and temperature change for the two processes involving 1 mole of an ideal monoatomic gas. A. 1,500 joule of heat are added to the gas and the gas does no work and no work is done on the gas. B. 1,500 joule of work are done on the gas and the gas does no work and no heat is added or taken away from the gas. Question number 3 is state the first law of thermodynamics and discuss its physical significance and limitations. Question number 4 is what are thermodynamic variables? And question number 5 is what is the concept of work in thermodynamics? On this slide, we take the references of the material. There are two textbooks here and three reference books.